Welcome back everyone to part 2 of trig equations. Last video we introduced the notion of a trig equation again, and we worked through a handful of examples that helped highlight a lot of the key components of solving trig equations. In this video we're going to continue working through a handful of examples where in particular we're going to utilize trig identities to help us solve more complicated looking trigonometric equations. To begin with, let's take a look at example 6. Here we now finally have multiple trig functions running around. And you might be inclined, when you look at this problem, to switch the tangent into, say, a sine over cosine. That's a potential way to go, but it might be more complicated doing it that way than you really need it to be. For example, observe that the tangent and the sine are only related by multiplication. So one way I could proceed is by moving everything to one side, and I could think of this as sine of x tangent of x minus sine of x is equal to 0, for which immediately your spidey senses should start tingling and you recognize, oh wait, sine is a common factor. So let's pull that out and we'll be left with a tan of x minus 1 left over. And just like we saw in the previous video, as soon as I have one factor times another factor equal to 0, I can use the zero factor property and set each of them equal to 0 independently. So in this case, I gain access to two trig identities, sine of x equals 0 or tangent of x minus 1 equals 0. Which of course I can move that minus 1 to the other side and simply think of that as tan x equals to 1. Solving the first trig equation here, what angles x from 0 to 2 pi produce a sine value of 0, that's not too bad. That's always going to be some of the quadrantal angles, and here we'll recognize that x is going to be 0 or pi. And you might be inclined to put 2 pi in here as well, but notice that 2 pi has been excluded in the original domain restriction. The harder one might be tan x equals 1, but if we write our quadrants A, S, T, C, and we see that tangent is positive in the first or the third quadrants, and we remember that tangent can be rewritten as 1 over 1, we see immediately that opposite over adjacent, the angle in question here is 45 degrees. So we see here that x should be either pi over 4 in quadrant 1 or 5 pi over 4 in quadrant 3. Coming together, these four angles serve as our solution set for sine x tan x equals sine x. So I hear you keep asking, where's the trig identities? Well, let's finally take a look at an example that highlights the use of one. Here we have 2 sine squared equals 3 cosine. Try as you might, even if you move the 3 cosine to the left, there's no amount of factoring that's going to help figure out how to sort of pull the sines and cosines apart. But remember, one of the rules that we set out in the very beginning was that, if possible, use identities to get the equation to only have one type of trig function. So we ask ourselves in this situation, is there a trig identity that relates sines and cosines and potentially their squares? And the answer, of course, is yes, the Pythagorean identity. So what I'm going to do is replace that sine squared of x with a 1 minus cosine squared. So this is equivalent now to considering 2 times 1 minus cosine squared of x equals 3 cosine of x because of that substitution. Now I can distribute the 2 and I'll get 2 minus 2 cosine squared of x is equal to 3 cosine of x. And now I want to pull all the, so first of all, I have only cosines. That's a good thing. Second of all, I want to pull everything to one side, and I'll opt to move everything to the right so that I can get a positive in front of my square. And after rewriting it and reorganizing it, I'll get 2 cosine squared of x minus 3 cosine of x plus 2 equals 0. And now I'm in good position, because now my equation looks quadratic-like and very similar to the ones we've already seen so far. Indeed, this will factor. It'll again factor into a pair of binomials where I'll have a 2 cosine of x and a cosine of x as the first terms of each of them, and then I just have to figure out what the constant terms are. And it turns out the right combination is minus 1 and plus 2. A quick foiling in your head will verify this fact. And in fact, a quick foiling in my head tells me this is not correct. Oh no, I have my own signs wrong. That should be a plus. So I get 2 cosine, I move it over there, I get positive 2 cosine squared plus 3x minus 2. So I had that a little backwards in my head. There we go. And now we have the right factorization. So therefore, this will set up two equations. Setting the first equal to 0 or the second equal to 0, I'll end up with cosine of x equals positive a half, or cosine of x equals negative 2. Solving the first equation, I'll draw a picture, and I'll get ASTC. Cosine is positive in the first or the fourth quadrants with an opposite or an adjacent over hypotenuse of 1/2. So that's 1, 2, 2 with a missing side of root 3. We recognize immediately that the reference angle for this one is equal to pi over 3. So the two angles in question for the first equation is pi over 3, as well as 2 pi minus pi over 3, otherwise known as 5 pi over 3. But what about this equation? Observe that this equation actually has no solution. This one is a completely busted equation because negative 2 is not in the range of cosine. Remember that cosine only has a range of negative 1 to 1, so there is no angle x that'll possibly give you negative 2. So this is just a busted equation, and that one is just irrelevant. We just ignore it. So the only answers to the question turn out to be pi over 3 and 5 pi over 3. So there are subtle tricky things like exactly that you have to look out for while you're solving trig equations. Throughout the video here, I'm sort of providing my take on it, which is a very streamlined take. While you're working through these questions at home, obviously you're going to run into small issues and stuff. As you run into them, come talk to me, send me emails, or ask your study groups what's happening. You don't want to sort of ignore some of these small things like cosine of x equals negative 2, because it turns out that those are pretty important. So here we use the Pythagorean identity to swap out sine squared for some cosines. Let's use other identities. For example, here we encounter an equation cosine of 2x equals negative sine x. The minute we see the cosine 2x, we immediately gravitate toward using some sort of an identity. The question is which one? You'll recall from the last few videos in chapter 5 that cosine of 2x actually has more than a few equivalent trigonometric formulations. We're going to voluntarily choose to use the one that's related to sine, since that's the other trig function that's here. So what I'm going to do is I'm going to replace cosine 2x with 1 minus 2 sine squared x. Those identifications are the same based on the double angle formula for cosine 2x. And apparently that's equal to negative sine x. And so now we can move everything to one side, make everything positive, the usual, and we should get 2 sine squared x minus sine of x minus 1 equals 0, which is again quadratic-like. It'll turn into 2 sine of x plus 1 times sine of x minus 1. And again, a quick mental FOIL will verify this fact. Each of these equations give their own mini equation, which will now be sine of x equals negative 1/2 and sine of x equals positive 1. The first equation might warrant a picture, so we have A, S, T, C. Sine is negative in the third quadrant and the fourth quadrant, where sine is opposite over hypotenuse. And therefore, clearly the missing side is √3, and the reference angle in question here is going to end up being pi/6, but since we're in quadrants 3 and 4, of course that means that the actual angle is 7 pi/6 and 11 pi/6. Whereas the second equation, sine x equals 1, there's only one angle from 0 to 2 pi that can produce a 1 with a sine, and that's going to be pi/2. So here we have our three angles that solve that equation. So we've utilized double angle formulas and the Pythagorean identity so far in terms of what identities help us solve trig equations. It turns out that the double angle ones are usually the most common ones that you'll run into when trying to solve trig identities, when trying to solve trig equations. So you should always be on the lookout for potential double angle formulas. Taking a look at the next example, we have sine of x times cosine of x is equal to negative 1/2. I really do encourage you to pause the video here and see what you can do about trying to solve this one on your own. And when you're ready, click back and then see how I proceed. Your first inclination might be to move that negative 1/2 to the other side, but I caution you against doing that. Additionally, there are no squares, which means the Pythagorean identity is kind of a bust. But remember, we do have access to other trig identities. For example, sine of 2 theta is equal to 2 sine theta cosine theta. So in this case, if I take this equation and simply multiply both sides by 2, what do I get? I'll get 2 sine of x cosine of x on the left, and then I'll get a negative 1 on the right. I don't like writing it that way. 2 on the left and a 2 on the right. We'll get a negative 1 on the right, and now 2 sine cosine can be replaced with a sine of 2 theta, or 2x I should say. That's the substitution we're going to make. And now it turns out this is an equation we can answer, noting that we want angles between 0 and 2 pi, and we see a 2x on the inside. We know that we don't want to just set 2x equal to the answer from 0 to 2 pi, which to get a sine of negative 1, ordinarily you do 3 pi/2. That's going to be insufficient. Because as we noted at the beginning of this lesson, if I multiply by 2 on the inside, I have to make sure to pick up more angles than I think I do, because once I divide by this 2, it's going to shrink all of the coterminal angles back into 0 to 2 pi. So instead, I'm also going to pick up whatever's coterminal to 3 pi over 2, which in this case is 7 pi over 2, by adding 2 pi to it. And you'll see that despite 7 pi over 2 clearly being bigger than 0 to 2 pi, we find that after dividing by 2, we turn it into a 3 pi over 4 and then a 7 pi over 4, for which we recognize, indeed, 7 pi over 4, these both are in 0 to 2 pi. So these are going to be our answers. So we see that the double angle formulas can pop up in mysterious ways. It's not always going from the double angle to the sines and cosines. Sometimes going the other way is also useful. So what about this next example? We have cosine of x minus sine of x is equal to a -1. Again, I encourage you to pause here and sort of tinker with this equation to the best of your ability. But the way to sort of think about this, in my opinion, is that your first inclination should be to move this -1 to the other side, and then maybe try to swap out the sines for cosines or something. But observe that we're running into the same problem we ran into in the previous one. There's no squares. If there were squares, we could probably swap out with the Pythagorean identity. In the previous problem, we were able to identify the double angle formula and then go from there. But I don't know, the double angle formula looks like it's going to be hard to fabricate here. But if our issue is where we don't know where the squares are, one way to proceed is to simply take a square. Just like you can add 2 to both sides or multiply by 5, you can also square both sides. So maybe that's an avenue to test out. Although this is a little late in the lesson, this might be a good moment to pause and point out again, just like we did with trig identities, you're not always going to get the right answer in your first try. It's important to be comfortable and remain steadfast and simply keep trying new avenues until you gain some traction. So in this example, we're going to try squaring both sides. If I square both sides, I'll get the left-hand side after foiling should give me cosine squared of x minus 2 sine of x cosine of x plus sine squared of x is equal to a +1. So cool, we found some squares. Maybe that's a good thing. What's more interesting is that the squares in question are cosine squared plus sine squared, which the minute that rolls off your tongue, you should recognize that that's going to be equal to a 1. That's the Pythagorean identity. So now we're getting 1 minus 2 sine of x cosine of x is equal to a 1. So the 1's are going to cancel, and I'm left with a -2 sine of x cosine of x equals 0. Now you might think that you're sort of in a worse off spot, but you're actually in a great position to solve this equation. You may be inclined, given that we just did a problem where we witnessed 2 sine theta cosine theta was equal to sine 2x, you might be inclined to see that here and immediately jump on it. However, that's actually making this way more complicated than it needs to be. So you can do that and you'll get the right answer. Or, what if you were to just divide both sides by -2? So this turns into now just sine x cosine of x equals 0. And then the zero factor property says that this says either sine of x equals 0 or cosine of x equals 0. Note that the property we're using to get from this line to the next line is called the zero factor property. You can look that up if you'd like. It's the zero factor property. Its name is indicative of when you can use it. You can use the zero factor property only when your product is somehow equal to a 0. Up above here, we see that it was equal to a -1. That's why we could not do that. But here it's equal to a 0, so therefore we can do this. A very common mistake I see students make is they get to, like in the previous problem, a line like at the first line here, and then they try to set sine of x equal to a -1 and cosine of x equal to a -1. And unfortunately, it's not called the -1 factor property. It's called the zero factor property. So in this example, we can do that, which means we're solving when is sine equal to 0 or cosine equal to 0. Of course, sine of x is equal to 0 at 0 and pi, and cosine of x is equal to 0 at pi over 2 and 3 pi over 2. So those are going to be our final answers there. To me, this question is really highlighting the power of what we're doing here. Who would have known that if I take a cosine minus a sine and set it equal to -1, that apparently that occurs at these 4 angles? Sure, once you know the answer, it's somewhat obvious, but before you know the answer, it's hard to know whether not only are these 4 answers, but why are these the only answers? These are interesting questions. The last example we're going to encounter is cosine of 2x equals cosine of x. This question should be reminiscent of an earlier problem. Remember on the previous page, we had cosine 2x equals negative sine. So, borrowing from our experience, we swapped cosine 2x for 1 minus 2 sine squared of x. But remember, we made that as a choice. Cosine 2x as a double angle formula has 3 different formulations, and we chose the one here that gave us sine functions. Once we're at this problem down here, because the other side has a cosine, we might actually choose to instead swap cosine of 2x out for a cosine variant. The cosine variant, if you go back into your notes, is 2 cosine squared of x minus 1. That's the trig identity that we're using. And apparently now that's going to be equal to cosine of x, which then if I pull everything over to one side, I get 2 cosine squared of x minus cosine of x minus 1 equals 0, which again is quadratic-like. So I'm going to end up getting a 2 cosine of x and then a cosine of x. Question is, what are the constants that make this work? And if you tinker around with this for a bit, you should get a +1 and a -1. And a quick FOIL in your head will verify that indeed this is the case. And so then the zero factor property kicks in and we should get 2 equations. We'll get cosine of x is equal to a -1/2 and a cosine of x is equal to a 1. This first equation, we can draw a picture over to the right. We have ASTC. Cosine is negative in the second and the third quadrants. -1/2 is the adjacent over the hypotenuse. The missing side is, of course, a √3. And so the reference angle that we're looking at for these reference triangles is pi over 3, meaning in quadrants 2 and 3, the answers to this first trig equation is going to be x equals 2 pi over 3. And then in quadrant 3, we have 4 pi over 3. Whereas the answers to the second trig equation is what angles x make the cosine of 1. And of course, the only answer to that would be x equals 0 and potentially 2 pi. But remember that our domain restriction includes 0 but excludes 2 pi. Because in this case, we don't want a whole bunch of coterminal angles. So we'll erase that. And our final answers are these 3 angles. So this example finishes off the collection of examples that we want to do in section 5.5, where we introduce and discussed trigonometric equations. In particular, this video, we talked about how we can use trig identities to help solve trig equations. Now, the only trig identities we really used were the double angle formulas and the Pythagorean identity. Yes, to solve more complicated trig equations, you can use all of the other trig identities that we developed. But for our purposes, we'll focus on just using those double angle formulas and the Pythagorean identities. So this should give you more than enough to chew on and to practice with. So go tackle all the homework problems related to this. If you have any questions, make sure to let me know. But otherwise, have a great rest of your day, and I will catch all of you later.